Okay, today I wanted to go over how I created this title slide animation. I got quite a few questions on it. Turns out that it's pretty simple to do, but I've probably picked the most inefficient way to do it. But I figured I'd go through today and kind of explain kind of the steps that I went through, how I put it together, just to satiate everyone's curiosity. So, first thing I did is I ran some optimization. So that's what that first 2D geometry is. And I had saved all of uh, the geometries from that optimization. So that's where all that kind of shape dancing around comes from. That's the optimization, optimizing kind of duct shape and rotor shape. Um, so I finished there on the last of almost the last state for the optimization. And then I took the axisymmetric data and rotated that and revolved it out into 3D to get all of this 3D stuff. So all of that work was done just in a script. So I picked things like the number of blades. It's far more than is actually in the optimization, but it looked cool. So added a bunch of blades. Decided I want a smooth animation, so I made it a frame rate of 60 frames per second. And then I just decided how long I wanted each thing to go. So that first optimization goes for 15 seconds. And then each little piece after that goes for about 3 seconds. And then the rotors spinning up and it flying around and stuff is another 10 seconds. And then everything kind of backs down in 3-second increments again. So with the optimization, I did actually cut it off. The full optimization ran about twice as long, but the changes to find the optimum after about 32 here are visually very, very small. So to just get to the interesting 3D stuff for the animation, I cut off the optimization frames at that point. And then I smoothed out the geometry. So the actual analysis geometry doesn't need to be as smooth as it does for kind of the aesthetics of this rendering. So I ended up refining geometries either in the 2D case just to make them fine enough, and then in the 3D case, the refinement was based on how many steps I needed to take to revolve things out or to loft things. So, for example, the number of duct sections around the circle in the 3D revolve is the number of frames for that process. I also used cosine spacing when determining a lot of the 3D geometries, just as kind of a subtle thing. You may or may not notice it, but as the center body is lofted out and as the duct is revolved out, it starts a little bit slow, speeds up, and then slows down as that section of the animation finishes. And that's just based on cosine spacing the geometry. So I went through and just for each of the frames, I saved a new geometry. So the 2D duct and center body, blades, all of that is just a different geometry for every frame. For the optimization, I did have to kind of refine the optimization states just because there was only 32, right? And so I interpolated between them for the sake of the animation to make it nice and smooth. I saved both the 3D files and 2D files for every time step. So I saved just empty files for times when the geometries weren't there. And that way I could have all the time steps line up in pair view, and it worked out nicely that way. The other thing I did is I have basically part of the 2D geometry present and part of the 3D geometry present as it's kind of sweeping through or unlofting or derotating. And so I have it as the 3D geometry is coming in, the 2D geometry is going out, and then vice versa in the opposite. So that's kind of how that sweeping and revolving process works. Other things here, I mean, there's not really much to it. I just wrote some functions that use the write VTK package in Julia to write VTK files. So it's just a bunch of grids. And for each time step in each of the feature generations, I just add more to the mesh. So mesh 1, nothing's in there. Mesh 2, kind of the first ring of whatever it is there. Mesh 3, add another ring, and so on and so forth. So that's how I kind of get that effect of lofting in, revolving in, the rotors growing, and then just standard, rotations and circles, really. That's really all there was to it. In pair view, I guess that's where most of the interesting stuff happens. So let's pull up maybe a more interesting frame. So kind of the secret sauce here is to use a camera. And what you can do is you can set your camera to interpolate between various camera positions. And so for each kind of major step in the not in the optimization, in the animation, I picked just basically a different camera position. So it starts, straight on, and then we rotate out and do a bunch of stuff. And then here, to get that kind of zooming out of the page towards you, I just zoomed in progressively further. And then once it gets all the way in, this actually I've flipped around, and I'm looking at the back, and then I zoom out. And so it looks like it's flown at you and you've gone through it, and then it's flying away, and then you're flying back to catch up. But really it's just a bunch of zooming and rotating and moving things around, and you just let the camera interpolate between all the views, and then at the end it goes back to this axisymmetric 2D view, and then when it loops, then it's in the same spot. So the camera is kind of that secret sauce there. The other thing in pair view is I turned on ray tracing down here. So I enabled ray tracing. It takes a while to render because you have to get your sampling pretty high to make it look really good. And then some other things I did here is I turned down the light scale so that it wasn't so shiny and reflective. I set the kind of the background to be a single color. The default, it looks kind of like there's like a floor and a wall. And I guess there is here, if you look really closely on the animation, you can actually see like a little seam right down the center, but it's really faint. So I didn't notice it actually at first. But I just set a white background. And then samples per pixel I set to 30 so that it looked really nice. And then other than that, not really anything in the settings. Once you turn on ray tracing, you have access to material property. So to make everything kind of match nicely, I added these custom materials, which is just in an Osprey materials.json file. This is in the PairView application directory. So I just grabbed, I actually grabbed the stainless steel and copied that, and then just changed the colors to match the colors that I used in my paper and the rest of the figures in my presentation. So that way the blue, green, and red all matched. I call them primary, secondary, and tertiary because in LaTeX, that's what I name them, so that if I change the colors, I don't have to go and rename everything. But yeah, it's pretty simple. That's really about all there is to it. The other, I guess, thing to note is in Keynote, this animation is actually the entire size of the slide and then is behind the text. So when it kind of zooms out at you out of the screen, it's able to fill this whole slide. So it has kind of that interesting effect that it feels like it's coming at you. Whereas in the closing slide, I just have it cropped in on just the animation part. So it still kind of like zooms out of this little page here, but on the title slide, it fills the whole slide. So yeah, that's it. Hopefully you learned something, and maybe you can find a more efficient way than I did to put something similar together. Thanks.